Well, this week we are going to talk more about math, okay? Different from last week. Last week is more about physics, okay? There are a lot of models and there are a lot of things that it's hard to understand because you need some intuition, physical intuition. But this week, well, we will go back to math. Hopefully you will prefer math, but well, also have to warn you that this week is about analysis, okay? So analysis means, well, you will need some basic knowledge about analysis, which is more than calculus, okay? It may be harder than your calculus course. It may be something you are going to learn in your real analysis course, but here we are going to use some of the results, and unfortunately, I don't have enough time to prove them, okay? So if you do have anything that don't understand, that's totally normal. You can either, well, choose to use it as a black box, or you can ask me, okay? Ask me about the proof or anything, okay? And this is something might be hard for you at the very beginning, but then you find that it's very interesting. It's really interesting. Yeah, this is why I really like analysis. Okay, so let's start. Well, last week, we discussed and said that eventually what we are interested in this semester are only 4 types of important PDEs, right? And last week, if you ignore those kind of like well-postness or initial data, those kind of thing, or how you can get those PDEs, what we've learned is only one thing, right? We only learn what is a transport equation and how we can find the solution of a transport equation. And it seems pretty easy. As long as your transport equation is just a linear equation, and as long as your transport equation is just have 1 dimension in time and 1 dimension in space. Okay, 1D transport equation. And I hope, well, after you did your homework, I hope you are able to understand this part. And now what we are going to do is we are going to switch instead of this, first order partial differential equation, we are going to do our second order partial differential equations, okay? Which is heat equation, Laplace equation, and also the wave equation. Okay, these 3 kind of differential equations. And the difference between these 2 kinds of differential equation is this is only first order differential equations, but these are second order differential equations. But again, we only study, although at the very beginning, I thought maybe I should introduce some nonlinear differential equations to you, but it seems that you don't really like this kind of transport equation stuff. So, well, maybe we'll just skip that part and discuss about everything just linear, okay? Nothing nonlinear in this course, okay? And, well, first of all, again, just like the transport equation, maybe we should try to find the solution first. Although eventually you will find that finding the solution for a differential equation doesn't really make sense. But at this moment, what we can do is, since we are trying to deal with really simple differential equations, sometimes we are lucky and we are able to find the solution. Okay? Question? So let's try to do that. But maybe before we do that, there is another thing we should discuss about, which is we only discuss three kinds of linear second-order differential equations. Well, then you may think that, okay, we are trying to solve, if we are trying to solve the second-order linear differential equations, then there are a lot, right? Not only for those kind of heat equation or Laplace equation or this wave equation. Well, these are just some really simple ones, right? These are really simple second-order linear differential equations. But then, what if we have something in general? What if we have some kind of differential equations like this? Let's say we are in 1D in time, and well, maybe let's not say 1D in time because we are discussing the Laplace equation. Hello. I guess maybe I should mute you. You can mute yourself, well, if you want. So maybe let's discuss something simple. Let's discuss something, for instance, we are only in 2D, which means you are discussing U that only depends on X and Y, and see what happens if we only have this, well, some functions, some differential equations about U, and U is from R2 to R, okay? And if it is something like this, then what we have is we may have some general form of the, well, second order differential equations. Like we may have A11 UXX, right? Plus A12 UXY, right? You may have UXY and UYX, but as we said before, we will always assume that UXY is equals to UYX, okay? So let's put 2 here just for simplicity, okay? Means you have 2 terms here, UXY and UYX. And you may have the, well, A22 UYY and plus, say, A1 UX plus A2 UY plus A0 U equals to 0. Okay? So this is a general form of the second order partial differential equation of 2D. Okay? You can see that it has every term that you want. And for simplicity, let's even assume more. Let's assume all the coefficient does not depend on X and Y. Okay? Everything just a constant. Then this is the general form of the constant coefficient second order linear differential equations. Right? And okay, so let's assume you are able to solve this kind of differential equations like heat equation, Laplace equation, and wave equation. Then the question is, can you generalize your results to this kind of general type of second order linear differential equation? The answer is yes. And this is so-called the classification of second order, well, linear differential equations. Okay, so which is something like a, well, can say that as long as you tell me the different value of A1, A11, A12, A22, then I can tell you what kind of equations, what kind of basic equations have the same or similar properties as yours. Okay? And I believe that nobody in this class, have learned the analytical geometry. Which is why you may not familiar with this kind of change of variable, well, operations. Okay? So basically, what I'm going to do is I'm going to set up some other variables. Set x equals to something c something eta. Okay, y equals to something c something eta. And then we will change our independent variables of this differential equation from xy to c eta. Okay, c and eta, since most of you, I think, are using the text, so you may know that these are just Greek letters. And maybe you want to put some number here, C1, C2, C3, C4. Okay, then this is a well-defined change of variable. But then the magic here is, well, as long as you have this kind of differential equations and you do this kind of change of variables, you may check that eventually you can find some suitable C1, C2, C3, and C4 so that you can make this kind of differential equations simpler. Okay, and this is somehow related, as I mentioned before, this is somehow related to the analytical geometry, which is, well, we can somehow think this just like the characteristic equation method. Okay, just like that. You can somehow think is this kind of thing, this A11 x, well, uxx can somehow will transfer to some algebraic equation, such as A11 s squared plus 2A12 st plus A22 t squared. Okay, and maybe plus A1s plus A2t plus A0 equals to 0. Okay, then, well, for any this kind of differential equation, you somehow makes it like an algebraic equation, right? And if you have learned the analytical geometry, you may know that then what you can do is you can try to change it to a canonical form or the standard form. And well, for this kind of second order surface, well, surface of dimension 2, there are only 3 kind of things eventually you can get. One is something like an ellipsoid, well, ellipsoid or circle, something like an ellipsoid, something like x squared, a times x squared plus b times y squared equals to 1. Okay, and well, this is like an ellipsoid, like this. Or you can get x squared, a times x squared minus b times y squared equals to 0, equals to 1, right? This is a hyperbola. Probably I can, well, I don't want to rotate it, but this hyperbola is something like this. Okay? Or it may be something like a problem. Something like this. Okay? So this is something, well, you are more familiar with, like this. It's a quadratic curve. Okay? So eventually you find that your curve, maybe I should say this is S, this is T, but let's abuse of this notation a little bit at one moment. Then you can do some change of variables of S and T so that it can be either this one or this one or this one. 3 times of well, second order or this well, some second order curves. Okay, there are only 3 kind of. And how you can change this kind of thing to this kind of standard form? Well, the only thing you need to change is you try to do a linear transformation from st to xy or from xy to c eta. Then you can find that eventually you got this kind of thing. Okay, you can try to check analytical geometry books and see in general how you can do this and how you can do this in, for instance, 3D. Okay, that's well, it's relevant to the matrix. It's relevant to the, well, matrix theory or linear algebra. It's relevant to the eigenvalue and eigenfunction. Okay, which is something like you can somehow connect this to a matrix. The matrix is formed by A11, as we write it like this, A22, this is this term, A12 and A12. It's a symmetric matrix. Okay, and then what you want to do is, well, you can see that if you do a change of variable, either, well, x is c1 c, c2 eta, y is c3 c, c4 eta, or s equals to something like a1x, a2, well, whatever y, and well, t equals to some x plus some y, then if you try to map this kind of, well, change of variable to the matrix representation of this equation, then what you will find is, suppose this is a matrix A, then what you will find is, then the matrix, the coefficient of this well, algebraic equation or of this well, differential equation will be changed to A times B transpose. Okay, and you find that. And then in that case, you will see that, okay, as long as we can find some B, such that B times A times B transpose makes this matrix A to be a diagonal matrix, then we can make this kind of algebraic equation to these three kind of forms, right? Because that means you only have second order term, or your second order term has 1, 0, then you only have this second order term and the first order term. Okay, maybe you will have some additional term, but that doesn't matter. That's just some translation. Okay.
Oh wait, can you explain like a little bit more? So basically, when we're doing this matrix, we're only including the second order terms, right? And we kind of have the first order term like on left. And I see how we can like diagonalize the matrix to get rid of like the product of uxy, but like what are you gonna do with like everything else, like the first order terms?
Yeah, how we can deal with the first order?
We have learned that before in linear algebra.
Oh, I see. So you do it again.
Quadratic form.
We can just do a translation, right? So not so hard, just a translation. And we can make them perfect square, and that's the end of the story, right? So
and then,
doesn't matter, right? First order term doesn't really matter. But of course, this is only for the algebraic equation. If you want to check for the differential equation, then the first order term may matter, okay? So that you may have to deal with it a little bit more. But whatever, eventually we will see that it will somehow looks like this three kind of thing, okay? As long as you can find B such that it can diagonalize your A. So can you find B diagonalize A? Well, if it is in higher dimension, maybe this is a little bit harder because I don't think in your linear algebra course, maybe you have learned that the orthogonal matrix, okay? How you can make a matrix, a diagonal matrix by using the, well, orthogonal matrix. Well, as long as your matrix A is symmetric, then this is always possible. But here, since we are only in 2D, so we can even, well, make it simpler so that we can just ignore every other step, and I can write it down for you so that you know what is the linear transformation you should do, okay? But whatever it is, you can see that eventually you can change it to the standard form. So you have to, before you change it to the standard form, you have to say, okay, which standard form your matrix can, well, your differential equation can be, right? So this is actually a theorem. First, if, let's look at our differential equation. If you have such matrix, A12 square is less than A11 times A22, or the determinant of your matrix is greater than 0, okay? Or that simply means eventually your eigenvalues of your matrix are of the same sign. They have the same sign, either both positive or both negative, okay? In this case, your differential equation can be reduced to can be reduced to the form like Laplace equation plus something of lower order term. That's a lower order term, okay? Which is the term that only take first derivative and no derivative, okay? You can change it by doing some change of variables and make it like this, okay? So for this kind of thing, it really looks like your ellipsoid, right? So this kind of differential equation, we call it elliptic differential equation, elliptic second order differential equation, okay? And then, as you can imagine, if the determinant equals to 0, if the determinant equals to 0, then what you can do is you can change it by, well, to uxx plus some lower order term equals to 0. Okay? Which is also no surprise. And this kind of differential Yeah. I don't know what happened. Let me see. Let me see what happened. Okay, does it work now? Does it work now? Okay, I hope it works now.
Yeah, I think it does.
Yeah, okay, anyway. So for this kind of differential equation, we call it parabolic differential equation, parabolic type of differential equation. And lastly, as you can imagine, if a12 square is greater than a11, a22, or you have two eigenvalue with different sign, then we eventually can change it to be uxx minus uyy plus lower order term. This is so-called the hyperbolic equation, hyperbolic type of second order linear differential equation. Okay, it just well, the name just came from those kind of well, analytical geometry. Okay, nothing more than that. And the proof is actually pretty easy if you are familiar with linear algebra. But if you are not, then I can even write it for you, because it's only dimension 2. So for instance, let's say if you have a12 square is less than a11, a22, which is an elliptic case, okay? Then without loss of generality, we can divide a11 both sides, okay? Because a11 is a positive number. So we can assume a11 equals to 1. We can divide a11 and make it 1 and doesn't change anything else, okay? And then in this case, that means we have that a12 square is less than a22, okay? So in this case, we can do something like a perfect square, just as we did for the ODE as well, operators. What we can do is partial x plus a12 partial y, this operator square acting on u plus a22 minus a12 square well, times partial y squared u equals to 0. And maybe plus some lower order term. Okay. So this means, well, if we do some change of variables based on these two terms, we are done, right? We can make it like an elliptic equation as a Laplace equation. Well, the linear transformation is like this. We set x equals to c and y equals to a12 c plus b eta, and b equals to square root of a22 minus a12 squared. Okay, so basically it's like the inverse of the matrix of this one. 1, a12, and a22 minus a12 squared with square root, something like that. Okay, and if you choose your change of variable this way, what you find is, well, partial c u x y, just in case you are not familiar with this, well, this kind of change of variable, is equals to what? Is partial c u x is c. Y is a12 c plus b eta. Okay, so you can use the chain rule and makes it well, partial x and plus, well, a12 partial y acting on u. Okay, this is partial c is this operator acting on u. This is just chain rule. And partial eta u x y is the same. Partial eta u c a12 a c plus b eta, which equals to b partial y u. So, which is why the differential equation you have is partial c squared u plus partial eta squared u plus lower order term equals to 0. Okay, you don't need to memorize this kind of thing. The only, well, because we are only interested in dimension 2. So if you are not familiar with this kind of change of variables, you just set up those 4 numbers. Well, what is x equals to some c some eta, y equals to some c some eta, and then you just try and error. Okay, you just need to plug in and see what kind of what kind of coefficient can make you something you want. Okay, and similarly for this for the parabolic and hyperbolic case, they are the same. It's just some change of variables, and it's not so hard. So which means, if we are familiar with, if we know everything about the heat equation, wave equation, Laplace equation, we are able to solve almost every kind of second order linear differential equation. Okay. By the way, so in case you are interested in this kind of differential equations, the elliptic equation and parabolic equation are somehow highly related. Okay, their properties are very similar. And well, there are a lot of people who study this kind of differential equations. Although it's kind of boring, but it's still a very nice field if you are interested. Okay, for people who study elliptic equation, I know a lot of people studying it. For parabolic equation, it's basically my research area. But for elliptic equation, they study very hard on this kind of elliptic equation, and I can talk nothing with them because it's too complicated. And for hyperbolic equation, it's another story. Well, currently, as far as I can see, I would suggest you to well, if you go to US, maybe you shouldn't concentrate on hyperbolic equation. Although it's a very nice area and there are a lot of very nice results on this area, but it's well, it's at least nowadays it's very hard to find some job based on the research on hyperbolic equation. I don't know why. I guess maybe it's over too hard. So there's nothing very exciting for this hyperbolic equation, or the result of hyperbolic equation over too hard for non-expert. But anyway, yeah. So this is just some comments. So we can see that the reason why we're interested in the heat equation, Laplace equation, and wave equation are simply because that means every equation of second order, any linear differential equation of second order, okay? And as a byproduct of what we learn, of what we have studied, as a byproduct, there is an example to see, well, why this kind of change of variable sometimes can help us. Okay, for instance, about the wave equation, let's use xy instead of tx as we always use, just because we are going to change the variable soon. Okay, so this is a very typical wave equation. So if you try to solve a wave equation, you may find that, well, you may have no idea about how to solve it. But if we try to do a change of variable, there is one type of matrix that is similar to this matrix, but it makes the partial differential equation much easier, okay? Which is, you can see that this matrix is similar to this matrix, okay? Then, if you can change your differential equation from this type to this type, what kind of differential equation you will have? What is the corresponding differential equation to this matrix?
Oh, is it
It only
like
has one term.
Yeah, you only have one term.
Partial yu.
Yeah, it's partial x, partial yu equals to 0, right? This is some type of very little type of differential equation, partial differential equations that we are confident about, right? We are able to solve explicitly. So suppose we try to do a change of variable, the c equals to x plus y over 2 and the eta equals to x minus y over 2. What we will find is this differential equation actually can be changed to partial c, partial eta, u equals to 0. Okay, and from last week, from the first class of this semester, of this session, we know that u c eta should equals to what?
The addition of two functions, two single variable functions.
Yes, that's right. It's fc plus g eta, right? Or uxy is equals to f x plus y over 2 or not over 2, it doesn't matter, right? We can change this function plus g x minus 1. Okay, so we are able to find the general solution for the wave equation simply by changing of variables. Okay, any question about this part? Any question?
It seems that this solution, the form of this solution is unique.
Well, the form of the solution, it can be unique, but you can change this this kind of form of solutions, right? And you can change it to the initial data and boundary data, right? Represented by those kind of information, which is something I'm going to write it down for you. So, which is, you know that u, for instance, let's change xy to be xt, okay? Well, u xt is equals to f x plus t plus g x minus t, okay? And for instance, you have this kind of general form of wave equations, general form of solutions of the wave equations. And remember, what do we want? We want to solve the wave equation based on the initial value, right? Initial value and maybe the boundary value. So if you want to solve it based on this initial value and you assume that your x is in the whole space, is in the whole x-axis, then what we will know is, for instance, the initial data could be ux0 equals to little fx and ux0, not really x0, partial u, partial t, because this is like the acceleration is equals to something, so you should know the initial position, initial displacement, and the initial velocity, right? And x, 0 is equals to g of x. Based on these two information, we are able to find what is f and what is g, right? What is f? Well, you can see that from the first condition, you plug in 0, you should get fx plus gx is equals to little f. Based on the second condition, you have to take partial t here, right? If you take partial t, you get partial tf plus, well, actually minus partial tg, right? So it's f prime x minus g prime x equals to g of x. You take the derivative in terms of t and plug in t equals to 0. You got this one. Right? Is that clear? So we only need to solve this f and g. Well, that's not a problem, right? For the second equation, we can take the antiderivative both sides, and then, okay, it is just f minus g is equals to the antiderivative of g. So which means you will have f should equals to f x plus the antiderivative of g and divide by 2, maybe plus some constant. Right? And, question?
Wait, how did we get that?
The constant should be the function of t, right? Or the function of x, or because
the function should be what? You see? We find the antiderivative both sides. So that means you have fx minus gx is equals to this one plus some pure constant, right?
but it didn't you take in
It
the
doesn't depend on
with
t.
respect to t.
But this two equation doesn't depend on t. You see, this two equation does not depend on t at all. These are just some algebraic relation between f and g, capital F and capital T.
I think what Lancelot means is that we taken the derivative according to t. So if we would want to take an integral, we probably would.
Be careful here. Yes, be careful here. I know I got your point. Be careful here. This f and g are just a single variable function. They are not multivariable functions. So if you take this whole thing in terms of t, it's just this function take derivative and minus this function take derivative by chain, right? And since they are just a single variable function, so the derivative is just a derivative.
Yeah, for sure. Thank you.
With respect to the single variable of these functions. Okay? So which is why there's no t, absolutely no t. Because this is just the initial condition. You need to find them in terms of initial condition. It shouldn't depend on t, right? So then g is fx minus this one. Maybe plus c2. Right? So that means your u is this form, uxt must equals to 1/2 fx plus t, well, plus fx minus t, plus 1/2, you take the integral from x minus t to x plus t, g of y dy. maybe you should plus a constant c, but then you find that if you plug in t equals to 0, you find that c should equals to 0. So which means c1, c2, well, if you do this kind of operation, it cancels. Okay, so this is the general form of your solution of wave equation based on your initial data. And this is so-called the D'Alembert solution. Okay. Any question? Any question?
Before we move on, can we look at some examples about the change of coordinates? Like we can go through some properties.
What do you mean? The change of coordinates and property?
Maybe we can show some properties of the elliptic shape or parabolic shape or other shapes.
Oh, that's actually something. That's actually something not really relevant to our course. Well, okay. So let me take it this way. Okay. So in our course, you don't really need to understand those kind of change of coordinates. I try to write it down simply because you are supposed to know this, and you can use it here. Okay. But of course, I don't think I will really ask you to do this kind of change of coordinate and to simplify any differential equation. Okay, this to make you understand that we only discuss this three type of differential equation, but it makes sense. Okay, and this part for this change of variable part, I recommend you to read some textbook by yourself, but this is not something easy, okay? This is actually one of the key part of analytical geometry course. So for this part, you can try to read something by yourself. I can also recommend you some reference for you to read it, okay?
Okay.
Mm-hmm.
Thank you.
And, yeah, and this kind of change of variable stuff, well, I would say this kind of linear algebra. Okay, so if you don't understand it, if you are quite confused about it, then well, you can just ignore it, or you can just try and error. Okay, because this is not really something that should be in our course. Okay, because after all, we are an analysis course, not an algebra course. Sorry about that. Okay.
Sorry, before we move on, can you explain again about the proof of the theorem, like on the second line, for the proof of the theorem?
This one?
No, like the other page, the other half of the page.
Oh, okay. This part, right? This part. So for this part, what you're trying to do is you try to, again, write your differential equations as some operator acting on you, okay? Like a11 partial xx plus 2a12 partial xy plus a22 partial yy, this part acting on you, okay? Then you try to complete the square here. If you try to complete the square here algebraically, okay, then what you find is this one.
Oh, okay.
Does that make sense? So it's nothing fancy. It's pretty easy. It's just something like, well, as long as you know how to do this, how to solve this kind of problem, how to solve this kind of algebraic problem, then you are able to solve this corresponding partial differential equation problem. Okay, this is just a very simple trick, which I hope you could do it in the future. But for this course, For this course, it's okay because this is only a very small piece. Okay.
Okay, got it. Thank you.
Any other question? Or whatever it is, we eventually got the general form of the solution of wave equation. It seems that we almost finished 1/3 part of our course, or maybe, well, half part of our course. We study 4 kinds of differential equations. We find 2 solutions. Then the rest of this course seems to be find the rest of these 2 equations, find the general solutions, right? However, things are more complicated than you thought. Okay, and the reason we want to discuss more about this kind of differential equation is simply because, well, partial differential equation is harder than the ordinary differential equation, not only because, well, it has a lot of different kind of differential equation, partial differential equation, but also the initial condition and boundary condition sometimes may be some hard part of your study, of your, well, solution. So here, if we only study this kind of differential equation with initial data, then on the whole space, say on R, then this seems to be very simple, right? You can just plug in your initial data, and then you got your solution. However, sometimes we do need to find a solution based on the boundary condition. Like the example we have last time, you have a string here, and you try to make it oscillate. Then this is not an infinite long string, right? This is actually a finite long, the string of finite length. Then, if you try to describe it, the problem is you will not only have these 2 conditions. You may have some boundary conditions here and here, right? So in this case, you may need to have some other method in order to solve this partial differential equation. Which is another method, is so-called the separation of variables. Okay, what is separation of variables? Well, you can see that your uxt eventually seems to be really nice, right? It is just a function, it's just a summation of 2 functions which only depends on 1 variable. 2 single variable functions. You have addition, right? So here, if you try to solve the wave equation, let's imagine something very good will happen for the solution to your differential equation, which is, what if your u is not really a function that depends on 2 variables? What if your u can be written as the multiplication of 2 functions, and well, these 2 functions, one only depends on x, another one only depends on t. What if you have this? Then it seems that the problem becomes much simpler. Okay? By the way, starting from here, I forgot to mention this. Starting from here, what we are going to discuss everything on Stan's book. Okay? On Stan's book. And from this week to next week, the 2nd week and the 3rd week, what we are going to discuss are, well, something a little bit, very little bit on chapter 1 and chapter 2, chapter 3, and chapter 5. Okay, hopefully we can finish chapter 5, but if we do not have enough time, we will try to finish chapter 2 and chapter 3 of Stan's book. If you want to do some preview, you can read it. Okay, you can read the chapter 2 and chapter 3. So here we use a method so-called separation of variables, which is we assume that your function looks pretty nice, which is phi x times psi t. Okay, this is phi, this is psi. Again, Greek letters, just some letters.
Yes. Do we assume it's like nice, and then we try to find like something that looks like a diagonalization method to make them separate?
Yes, this is an idea at least, right? We can assume they are nice and eventually find, okay, it may not as nice as we want, but then we try to make it as close as we want, okay? Well, let's see what we can find. Okay, let's see whether this kind of assumption is available, at least for some kind of initial data or not. Okay, let's try. Or maybe let's first see why this can simplify our work, why this can make life easier so that we are able to solve it. If you do have this, then what happens? If you plug in, what do you find? You find that, okay, the right-hand side is just a phi x times psi double prime t, right? Left-hand side is just a phi double prime x psi t, right? It seems still not very easy, but what if we divide this, we try to put everything on t, everything depends on t to the right-hand side, and everything depends on x to the right-hand side. Okay, let's assume this both are not equals to 0. Not, well, identically equals to 0, otherwise u equals to 0. This, well, it's not interesting. So from this differential equation, what do you find? What can you conclude?
The constant.
There must both be constant, right?
Yeah.
Because the right-hand side is a function of t. Left-hand side is a function of x. What function could be both a function of t and a function of x? Well, it can only be a constant. Let's call this constant lambda. Okay? So that means we change our PDE to 2 ODEs. Okay? I believe, well, you are able to solve these ODEs. And I think Hu Yue asked us last time, maybe last Tuesday, well, there is a model you have learned before. That is like the spring model, right? You have a spring here, and you try to stress it. You try to stress it, and then by Hooke's law, you know how it will behave, right? And you know how it behaves simply by solving a second order ODE like this, right? But maybe there is another problem if you have learned this ODE course rigorously. That is the sign of lambda is actually crucial, right? If lambda is positive, then what does that mean? If lambda is positive, what does that mean? What's the solution looks like? What was that? If lambda is positive, what should be the solution looks like?
I think it has something to do with explanation.
Yes, it's something like explanation, right? It's just an exponential of square root of lambda times t, or the exponential of square root of lambda times x. This kind of solution, right? And plus minus, well, exponential of minus square root of lambda at t or x. So which means the solution of this type, if lambda is positive, if lambda is positive, then what we find is, okay, what we'll find that is C, which is a function in t, is a times e to the square root of lambda t plus b e square root of lambda minus lambda, well, minus square root of lambda t, okay? And so does phi, okay? However, if you try to look at this picture, okay, we try to make this string perturbed, then what happens is probably it will oscillate. It will not really decay as an exponential function. It should oscillate. Okay, it should change from big, well, at least it will not be monotonic function. If it is a monotonic function, then that means, okay, this point will go higher and higher, or at least eventually it will become higher and higher, right? Which is something that doesn't really make sense. So, which means physically, we don't really like this kind of solutions. So physically, it doesn't make sense. Okay, so we want, and you will also see that if you have this kind of differential equation, if you have this kind of solution, it will never satisfy your initial condition. Okay, so what we want is lambda is a constant that is less than 0. Okay, then what we will find is the CT is equals to a times cosine square root of lambda t plus b sine square root of lambda t. Okay, I mean minus lambda. Or you can also say that, okay, that means it's e to something square root of lambda. Here the square root of lambda is an imaginary number, which is why you can write it this way. Okay, so that looks pretty nice. So that also means you have phi of x is a cosine square root of minus lambda x plus b sine square root of minus lambda x. Okay, that looks pretty nice. Pretty nice. Then let's try to see what happened. Let's try to see, well, before that, let's, for instance, let's make the notation slightly nice. Let's call m squared equals to minus lambda. Okay, so that we can say this is m, this is m, this is m, this is m. M is just a real number. Okay. Now, let's try to see what happens. Let's try to see what happens if we involve the initial condition. Let's say you're in, well, the boundary condition. I mean, let's say the boundary condition for this problem is u at 0. Well, we have two fixed points hanging on this two walls. Okay, u xt equals to 0. Well, u0t equals to 0. u lt equals to 0. Okay, these 2 points, they are fixed points. And since we are dealing with some sine cosine, so maybe that's to make life easy. Let's say this is not L, this is just a pi. Of course, it doesn't matter whether it's L or pi. You can just change this, this m by multiplying this pi over L or whatever, okay? So let's assume your boundary condition is this type. Then let's see what happens. This means no matter what t you have, if you plug in x equals to 0, you should get 0. If you plug in x equals to pi, you should get 0. What does that mean? That means m must be an integer, and a must equals to 0. Right? So that means we do find a sequence or a family of solutions that can solve our wave equation with this boundary condition, this physical boundary condition. Um can be written as something like am cosine mt plus bm sine mt times some other constant, which can be, well, we can put this constant, this b constant here, and times sine mx. Okay, so these kind of functions are solutions. Are solutions to our boundary value problem. But of course, this is not enough, right? Because as a wave equation, we see that you are in the bounded domain, so you have the boundary condition. That's totally fine. But whatever you have, since you have UTT here, you always need to have the initial condition, right? So which means you want to find u such that u x0 equals to some function that we are given, and partial u partial t at x0 is some other function that we are given. Okay, and of course this f and g should satisfy f0 equals to f pi equals to 0, g0 equals to g pi equals to 0. Okay. Okay, so that means this type of this kind of solution may not be good enough because we want f and g to be arbitrary. But here, what is your general solution? Well, if you want to call it general solution, then what does it look like? Well, it looks like if you plug in t equals to 0, it's just am times sine mx. But we know that there are some fx such that it satisfies this condition, but it's not equals to sine mx. Right? It's not equals to sine mx for some integer m. Oh, this is a problem, right? Then how can we solve this initial value problem with the boundary value like this? You have any idea?
Wait, so can you outline again what we have to do?
What we want to do is we want to find some u such that it solve this differential equation, satisfying this boundary condition. Okay, and also satisfy this initial condition. Well, this kind of solution satisfy the differential equation, as we show, satisfy this boundary condition, as we try to improve, but it doesn't satisfy this kind of condition, right? What we want is whatever initial condition I gave you, you have to find the corresponding solution. This is what we want, right? This is what we want to in order to solve a differential equation. But here, you cannot say that if you give me fx is something like sine mx, then I can solve it. If you give me some other kind of fx, well, then I don't know how to solve it.
Can we try to improve on A and B?
Well, you can see that if we try to improve A and B and to make it somehow similar to fx, right? Then what we can do? What we want is at t equals to 0 is what? This term disappears. This term is still 0. It's am sine mx, right? So which means if you only get stuck on this kind of solutions, you may ask, your initial condition fx must of this form. It cannot be any other form, right? But of course, I can set up my fx to be, for instance, well, my fx initially could be something like this. Right? This is what? This is like minus, well, I think it should be minus x minus half pi square, maybe plus something, plus 1/4 pi square. This function satisfies this, and well, f pi equals to f0 equals to 0. But of course, this function is not of this form. And it's quite different from this form. Then how can we make use of our solutions? Try to make it in general. Any idea? Do you still remember? Since we are discussing the linear partial differential equation, right? So it has
The
superposition principle.
explanation.
Yes. Although, well, any single one cannot be of this form. What if we try to make a linear combination? And is that possible? If we try to make a linear combination, then it can approximate this fx and gx. Is that possible? So which means if we make a linear transformation, well, linear combination, since we have this constant here, m from, say, 0 to infinity, can this kind of thing evaluate at t equals to 0 equals to your fx?
That's where the Fourier series come from, right?
Yes. Well, we don't have any series, but we don't have any theorems. But here, what we want is, since every single one are solutions, so we make a linear combination, of course, is also a solution. So if we want to satisfy our initial condition, then that means we want to make some linear combination to get your initial condition. If that is possible, then we are done, right? So is that possible to find some kind of AM such that this kind of series can equals to your fx for arbitrary fx such that f0 equals to f pi equals to 0? Can we find such AM? If we are able to find such AM, then we solve the problem, right? Because AM, if you are able to find AM, then you can also, based on G, to find BM. Right? You just need another equation, which is M times BM. If you take the derivative in time, then you will get M times BM here, right? This is M times AM, but you have sign here. Then you plug in t equals to 0, the first term disappears. Only second term will left. So it's M times BM sine mx equals to gx. If this is possible, if you are able to find AM, then of course you are able to find Bm, such that Am, Bm will make your initial condition agree with F and G. Then we solve the problem, right? So the problem is, can we find such kind of Am and Bm? This is a very hard problem, surprisingly. Well, this is actually the main problem or the key problems in harmonic analysis, which is something we are going to learn, okay? The Fourier analysis or harmonic analysis. And this kind of method is a method that after this D'Alembert solution is the first, explicit solution for the first partial differential equation, as we mentioned, this wave equation. And after D'Alembert found these solutions, Bernoulli suggests that, for the physical problem, maybe we can try this way to find a general solution. And however, he was not able to convince Euler to agree that any function can be written in this form, like a power series, right? He cannot convince Euler. And later, Fourier, the Fourier analysis, Fourier did a lot of study and then make some progress about this problem. Okay, so now what we are going to learn is this kind of thing. Whether you are able to find this kind of trigonometry series to approximate an arbitrary function with this kind of condition. Okay? So, any question before we move on?
I have a question. So what we obtain now until now, we assume the solution can be separated into two different functions and their product. But what if the solution cannot be separated?
Yes, of course. In general, it cannot be separated, right? So of course, what we're trying to do is, we're trying to write the solution in this way. This way, right? From 0 to infinity. And if we try to find the solution in this way, you will see this solution is not separable, right? We say the solution may be separable if we are lucky. Unfortunately, in general, it is not separable. So what we try to do is, we try to find some solution that is separable solution, which by doing linear combination can approximate your solution. This is our idea, okay?
Okay, thank you.
Mm-hmm. Any other question? Any other question?
I have a question.
Mm-hmm.
I'm just confused by the following step after superposition principle. What did we do at the time?
What did we do where?
After superposition principle.
The superposition principle. Yeah. Mm-hmm. So the superposition principle just says that you can do any linear combination of solutions and you still get a solution, right? This is a superposition principle.
Yes.
Of linear equations. And here, what we do is we find a family of solutions. This family of solutions are both solutions, right? But here, what we want to do is we want to use this family of solutions to get a new solution such that it both satisfies our differential equation and the initial condition, right?
Yes.
And how can we do that? Well, the only thing we can do is we use the superposition principle and do a linear combination of the solution we find, right? We try to do a linear combination of the solution we find, and hope that this can approximate any solution.
Wait. I'm a little confused by the summation here.
Well, what do you mean?
The sum of the equation. Does it mean for any n or for any number of n's?
You see, for any number, for any integer m, it is a solution, right?
Yes.
Oh, so which means each single term of this guy is a solution. It satisfies our differential equation.
Yes.
And we wanted to satisfy our boundary condition. Yes, it does satisfy because each single term satisfies our boundary condition.
Yes.
Now, the last thing is, well, we want to satisfy our initial condition. This is the only restriction on this kind of thing. As long as it satisfies our initial condition, we are done. We find the solution, right?
Yes.
So we want to force it to satisfy our initial condition. And if you plug in, you find that, okay, that means we only want these two equations to hold. Okay?
Okay.
So that means we only need to find, given an f, as long as we can find am and bm, given f and g, then we are able to find the solution. As long as this, of course, this is a series of functions. The convergence is something we are going to discuss. But formally, you will see that, okay, each single term satisfies our differential equation, and each single term satisfies our boundary condition. So we only wanted to satisfy our initial condition. In order to satisfy our initial condition, we can play with this am such that this is an equation, and play with the bm such that this is an equation. And if that is true, then this uxt with this am, this bm satisfy initial condition, boundary condition, and our differential equation. So it is a solution.
I think to understand, but how can we make sure that each single one can satisfy the initial conditions since we use the summation?
Each single one will not be able to satisfy your initial condition, right? Each single one only satisfy your differential equation by what we are doing and satisfy our boundary condition.
Oh, I see.
Right. So combined together, it can satisfy our initial condition. This is a trick. This is a trick we are using. Otherwise, the problem becomes simple.
Okay, thank you.
Okay. Just a remark. Let me write a remark here. For elliptic equation, well, for parabolic equation, which is partial tu equals to partial xxu, we can use the same method. And you will find that, well, then the only difference is, well, you just change a little bit about your something like this, some terms here, okay? And we can still use the separation of variables to find this kind of solutions form, but then it will turn out to be the similar problem in some sense, okay? And well, I think we should have a rest now, and let's resume at 30, okay, 4:30. And then we will discuss a little bit about elliptic equation, because elliptic equation is slightly different, okay? Okay, so let's get started. So, as we mentioned last time, you can see that the only problem now is we're trying to find some expansion of the function f and g, right? We want to find some expansion. Expand this function by sine and cosine functions. So how could we do that? Before we introduce this so-called Fourier series, let me give you another example on the, well, on the elliptic equation. This is again a very important example. We may see it again and again in the future, okay, in the future this semester. That is, well, you have the elliptic equation. Elliptic equation is somehow hard, well, it somehow more relies on the, well, physical condition. Because here, if you try to study this elliptic equation, usually what we are going to give you is the boundary condition, no initial condition. Because physically, these are just x and y. So they are just on the whole plane, not t and x, right? So in this case, for instance, if we try to study this Laplace equation on the unit disk, okay, on a unit disk. And let's assume that your U is defined only on this this unit disk. Let's say this circle is C and unit disk is D. Okay, C is a boundary of D. Then, if we want to solve it, that means we want to solve the problem given the boundary condition of U. U restrict on C is equals to some function. Then this function is from the circle to R. Okay. Well, then the problem seems to be very complicated. At least what would be your F looks like would be a problem, right? This function is restricted on the circle, the unit circle. This is not so nice. If you try to write it in the sense of this x, y, then this is something not so clear for us. So if we want to solve a problem, a very typical problem like this, what we're trying to do, what we always do is we try to do a change of variable by this Cartesian coordinate to the polar coordinate. Okay. This is very easy. I believe everybody have learned this before, have seen this before. X is R cosine theta, Y is R sine theta. Okay, and this is actually an exercise for you. After class to show that this Laplacian operator under this R theta, well, this R theta coordinates, this polar coordinate, can be changed to the follows. Well, partial square U over partial R squared plus 1 over R partial U partial R plus 1 over R squared partial square U over partial theta squared. So the Laplace equation becomes this one. Looks very ugly, but we have to deal with it. Because then we see that U restrict on C is simply U with R equals to 1 and theta, which is a function on the unit circle, which means it's a function only depends on theta. Okay, this becomes a very typical, well, PDE problem, although the PDE looks very ugly. But the initial condition looks much better. Okay, then if we have this kind of thing, we can again do our trick about change of, well, separation of variables. Let's assume your UR theta is FR times G theta and see what happens. If you plug into this differential equation, well, it looks very ugly. But if it is separation, the variable separated, then this equation, this differential equation, will have only f double prime times r, and this is this term, times g of theta plus 1 over r f prime g theta plus 1 over r squared times f g double prime equals to 0. So we can do the same trick as we did before. We move this term to the right-hand side and then divide f times g both sides. What we will get is f double prime r, well, let's multiply r squared as well so that it makes it looks a little bit nicer. R squared times f double prime plus r times f prime divided by f is equals to g double prime over g. With minus. Okay. Well, this looks okay because then again, by the same trick, we know that it must be a constant. Let's say this constant is let's say this constant is again lambda.
I'm sorry, before it becomes too late. So why are we entitled to do it from the unit circle? And so like you take, or sorry, unit disk and you just have a net output that's a real number. And like why is that intuitively a thing we're doing?
Well, for this problem, it is particularly important in engineer, okay? Because for instance, you have some piece of material, a piece of metal. Then you can try to, for instance, study the temperature distribution of your metal. Then of course it has to be either some disk or something like some other shape, right? Disk is much simpler than other shape if you try to study it mathematically, which is why disk is always a very good example in order to study some general domain.
Oh, okay. So we just took a case of the way of a boundary, right?
Yes, we want to study some kind of boundary condition, boundary value problem, right? For instance, you may have some boundary, you may have some domain like this, but this kind of domain is over too complicated. We are not really able to study the geometry of this domain, right? It is somehow arbitrary. So if we try to make it regular, then this is the easiest case we can imagine. This is the first case we can imagine, right? And this is also a very useful case that we are going to study because it's useful in practice and it's easy enough. Okay. So we have to solve this differential equation. First one is relatively simple. It's g double prime theta, well, plus lambda g theta equals to 0. This one is simple. But the other one seems very complicated. R squared f double prime plus r f prime, well, minus lambda fr equals to 0. This looks not so nice. But first, from the first equation, we know that, well, first, g is periodic in theta, because g is nothing but a function defined on the circle. After you rotate for 360 degrees, then you go back, right? So g is periodic in theta, which means your lambda must be a positive number, right? Or maybe non-negative number. Then, if it is 0, then you got g theta is actually a constant, okay? Then, what you know is, well, then that means lambda is, again, m squared. Let's call it lambda squared. So you have g theta is, well, a times cosine m theta, let's say a tilde plus b tilde sine m theta. Or you can also try to write it by using Euler's formula. It's a e to the I m theta plus b e to the minus I m theta. Okay. Okay, so you got the form of lambda. You have the form lambda is actually m squared. So that means you can plug in here. You got r squared f double prime r plus r f prime r minus m squared f r equals to 0. This ODE is still hard to solve. But this is a homework problem and it has hint. Say that you take derivative, you got one additional r here. You take another derivative, you get, each time you take derivative, you get one additional r here. So it's very easy to imagine probably your f should be something like r to the m, if m is positive, or r to the minus m. So f could be r to the m or r to the minus m. Okay. Then, okay, if it is this case, then, and you don't want m equals to 0. If m equals to 0, you got f equals to, you got f equals to 1 or log r. Okay. Well, you have a homework problem to show this. These are the only solution to this ODE. Okay, and it has a hint. Don't worry. So it's not very hard. So we solve it. We got these two equations. Well, two solutions. So that means, okay, you may have this two kind of equation, two kind of solutions. But remember, we are studying the solutions on the unit disk. So which means if r goes to 0, your solution shouldn't blow up. Which means should be a bounded function. Which means you must have fr equals to r to the power m. Okay. Now we have again a family of solutions r theta is equals to r to the power m times AEIM theta plus BAM BMEIM theta minus. Okay. And again, well, if m equals to 0, then this one you should also discard, right? Because this one also blows up or equals to infinity at r equals to 0.
Sorry, but can you tell me again why when r approaches 0, fr should be bounded?
Because it is a solution. We want it to be a solution, which means it is well defined on the whole disk. If r tends to 0, then this function should tend to the value at 0. We're not studying a punched disk. We only study this disk. We're not studying the truncated disk. So which means u at 0 should be some real value. But for this one, if r tends to 0, it's equals to infinity for this one. So it is not a real value, so we want to discard them.
Okay.
It's just some kind of well, restriction about decay of your function. So we have again this kind of solution, and we want to satisfy our boundary condition So again, this becomes a very simple problem, which is you want to find AM and BM. Well, because this is from, well, this is for any M and this is for any M positive, for any M positive. So which means that's just to say is IM theta M from minus infinity to plus infinity. You want to find AM such that this is an equation. As long as you know that, as long as you can find AM, then you solve this differential equation, this boundary, well, Dirichlet boundary condition differential equation. Okay? Any question?
Sorry, can you please explain again why is lambda larger or equal to 0?
Why lambda is larger or equal to 0?
Yeah.
Because you see this G is a parabolic function. It's a periodic function, right? Because G is what? G is a function defined on this circle, right? G is a function defined only on the angle. But angle, we know that it's just a periodic. Theta plus 2 pi should equals to theta, right? The value of G as theta plus 2 pi should equals to the value of G as theta. Otherwise, it doesn't make sense. So which means if lambda is less than 0, then this G of theta should equals to what? Should equals to AE to the M theta plus BE to the, well, minus M theta. But this function, it can never be periodic, right?
Yeah.
You can say that theta plus 2 pi, where G theta plus 2 pi is equals to G theta.
Yeah.
Why we cannot have lambda less than 0?
Okay, got it. Thank you.
Any other question? So you see, we have two very similar problems. One is you want to find fx to be expanded by the trigonometry functions, or someone call it the trigonometry series. Or you want it to be expanded as this e to the im theta, but of course e to the im theta is nothing but trigonometry, right? Just trigonometry function. So after all, what we really want to do is we want to approximate a function by trigonometry series. Of course, no matter this kind of trigonometry series or this kind of trigonometry series, they can only approximate the periodic function. Don't forget this. So our main question now is how to use trigonometry series approximate periodic function. Okay. We are going to discuss about it for the rest almost 2 weeks, how we can deal with it. Because we can see that as long as we are able to know, as long as we have an algorithm to find this trigonometry series, then we solve our PDE, our Dirichlet boundary conditions PDE. Okay? This is so-called the Fourier series. Any question before we move on?
Yes, actually.
Mm-hmm.
When you are taking the Laplacian of u, as far as I can remember, Laplacian is like say u is a function of x and y. The Laplacian of u is a partial u partial x squared and partial u partial y squared. And in this case, we do the change of variables, and we change the Cartesian coordinates to the polar coordinates, and we the Laplacian with respect to r and theta. And why it gets this kind of result? I just tried compute a little bit, but I cannot get this result.
Well, you see, you have the second order of r's derivative, second order of theta's derivative, but then you will have something like the first order as well. This is something you have to do the calculation by yourself, okay? Because the calculation is just the change of variables, and I don't want to do it here, okay? If you want, I think you can also check check the Stan's book, the appendix. Let me see whether I can find it.
Maybe I applied the chain rule in the wrong way.
Yeah, probably you play with it in the wrong way so that you didn't get it. This is something I hope you can do it by yourself. Is there any? Unfortunately, I don't see. But
I had the same question as Lancelot, and I also got the wrong answer. So I don't like.
Actually, if I take the gradient and then take the divergence, I can get maybe the Laplacian. I think that will be.
You could definitely do that. Or if you want, you can try to compute what is partial r of u, okay? Because you have x, y, and the partial r of u is partial r of r cosine theta, r sine theta. Then you can use chain rule. And then to take it again, take the derivative again, and then you try to compute each term by term and do the addition. Okay.
Yeah, sure.
Or if you are familiar with this change of coordinates rules, then you can also try to use a matrix multiplication. Okay. Or if you want, I think you open any books of multivariable calculus, any serious books. I believe they have this kind of change of coordinate, or you can Google it. Okay.
Okay, thank you.
Mm-hmm. This is quite robust, I think. Any other question? Okay, now suppose we have we have an arbitrary function, but later, very soon, we will use some integral to compute this am, the coefficient of this series. So let's assume any integrable function. Everybody know what is integrable, okay? Which means this function is integrable with period (2 pi). Okay. Well, of course, you can assume the period of this function is L, but then that just makes this notation slightly confusing. So I will just simplify it as 2 pi. You can change it to be L. Doesn't matter. Say minus pi 2 pi. Okay, because other than minus pi to pi, it just repeats the value of fx. So as long as you know the value from minus pi to pi, you know this value of this function. Then you want f theta, because f depends on some variables that from minus pi to pi. So let's assume this f defined on a circle. Which means f only depends on some variable represents the angle, okay? Then what we want is this f theta is equals to this kind of thing. Here we use am, but here let's use an. we want f theta equals to this kind of thing. And then let's try to see for what kind of an it must be. Here, if we already have this result, then we may guess something like what is an. Okay, so let's assume you already have this f theta can be expanded by this an times e to the in theta. And now is something I'm not pretty sure whether you know this or not before, which is in what sense the right-hand side equals to the left-hand side. Have you heard about the term so-called uniform convergence? Have you heard about this term? Who
Yes.
heard about this term? You can raise your hand. Anyone else? Okay, only 2 of you heard about these terms, so maybe I should say what is this term. You may learn the Taylor series before, right? The Taylor series for an fx can be written as an x to the power n, maybe divided by n factorial. Let's ignore that. Which means you may try to write fx in terms of this polynomials and n from 0 to infinity. Okay, you always try to do this kind of expansion when you have a function. The reason is this kind of function, x to the power n, is much easier than an arbitrary function. Okay, when you try to take the derivative, okay, what is derivative of x to the power n? It's just n times x to the power n minus 1. What is the integral of that? It's just a 1 over n plus 1 x to the power n plus 1, right? If you are able to do it term by term, then it becomes super easy for this kind of, this is why you always try to write it, expand it by Taylor series. However, these two things, you may need to tell me what's the meaning of the right-hand side equals to the left-hand side, right? Because the right-hand side is nothing but limit. It's a limit as n goes to infinity, n from 0 to capital N, an x to the power n. So which means if you say this equals to this, then you probably say that for any x you gave me, this limit equals to f evaluated x. Right? This is what you mean. This is so-called the pointwise convergence, which, just as it says, given x, I know this sequence, this series converge after you gave me the value of x. Okay? But this kind of convergence is not good enough. The reason is, if you only have this pointwise, convergence, it is pretty hard to treat fx as the summation of this kind of functions. Pointwisely, it converges, but we don't have f prime of x is equals to the summation of an x to the power n, you take prime. You have the pointwise convergence for this kind of series, the Taylor series, but then that doesn't mean you can take derivative term by term and get another pointwise convergence series. Okay? And similarly, we don't have, you can take the integral term by term. this is also something we don't really have. Because when you try to do this kind of operations, you somehow take two limits instead of one. One limit is you take this n, capital N goes to infinity. Another limit is you try to take this, this derivative or the integral, which is also a process of limit. And unfortunately, if you only have this pointwise convergence, these two limits, you cannot change the order. If you take the derivative, that means you have this, you take this kind of functions, and then you minus the, you evaluate at x plus delta x and divide by delta x, and then take delta x tends to 0. Okay, so you first take n goes to infinity, then take delta x goes to 0. This is the right hand side. But the left hand side is you first take delta x tends to 0. Then you take the n, capital N goes to 0, goes to infinity. So these two sides, they are different by switching the order of limit, similar for the integral. So if you only have the pointwise convergence, you cannot change the order of limit. You cannot taking derivative by term, okay? But if you have some stronger assumption about the convergence, which is the uniform convergence, which defined by, well, probably I should define it in the language of epsilon delta, which is for any x in a domain of fx, say any x in R. Uniform convergence, this sequence, uniformly convergence to fx means for any x in R. Well, as long as you have, you give me given epsilon, we can find some capital N such that for any x in R, summation n from 0 to capital N, an x to the power n minus fx is less than epsilon. You see, uniform convergence is different from the pointwise convergence. Pointwise convergence says that for a fixed x, for each single x, fixed x, given epsilon, there exists n such that this inequality is true. But for uniform convergence, it doesn't care which x you have. We have a uniform big N, such that after this term, the rest are very small. Okay, the rest of the term are very small uniformly in X. Is that clear for the definition of the uniform convergence? You may have to digest it because you may forgot all this kind of epsilon delta language. Unfortunately, this epsilon delta language is very important in this course.
I think the uniform and pointwise convergence we have learned that in Math 205.
Oh, really? That's pretty good. But why nobody raise your hand and say you have learned that?
I remember in Math 205 we have learned the convergence radius of convergence.
Yeah, the radius of convergence, exactly. The radius of convergence is, well, on this radius, every x you have this uniform convergence for the Taylor series, right? I hope this can remind you somehow.
Yes, and I remember the example is 1 over 1 minus x, the Taylor expansion.
That's right. So the radius is just 1, right? You can compute it like that. And the good thing for uniform convergence is, well, for uniform convergence, maybe it's not x to the power n, but let's just use it as an example. It can be an to e to the in theta, or it can be some an fnx, okay? Equals to fx converges uniformly in x. If it is uniform convergence, then what we have is, if you take the derivative, you can take derivative term by term. Okay? And, well, maybe I should, I'll state it later. And from 0 to infinity, an, if you take the integral from x0 to x1, it is also, you can take the integral term by term, okay? So you can switch this limit. And of course, if fnx is continuous, so does fx. Fx is also continuous. So is, well, so is fx. So which means uniform convergence is really, really nice. You can really treat fx as some polynomial or as some trigonometry functions. Okay? And it is very nice, but how you can check some series is uniform convergence. In this course, I think we only need one criteria to check whether a sequence is uniform convergence or not. That is, well, suppose each term can be bounded about by some Bn. Okay, and we have the Bn, the summation of Bn converge, which means the tail of this sequence, the tail of your series, is uniformly very small, right? Because you know that this kind of sequence, this number sequence, is summable. And that means, well, after a lot of terms, the tail of the sequence are very small. Now, if this can be seen as an upper bound, then of course, the rest of these functions, after a lot of terms, the rest of the functions are uniformly very small. Okay? Then, and then we know that an, fnx converge uniformly. Okay? Well, let's say summation of an, fnx converge pointwisely. Do we need this condition? Well, I'm sorry. Actually, we don't need this condition. I'm sorry. Sorry about that. So as long as each term of your sequence is bounded, it can be controlled by a convergent sequence. Then this sequence, this function sequence is also converge uniformly. And then you can treat it as just as a polynomial.
The proof of this is like reduce it to a geometric sequence, right?
Exactly. Well, it's not really like a geometric sequence. It's just to reduce it to Vn.
Yeah.
Reduce it to geometric sequence is just for the radius, okay? The convergence radius. You can reduce that to the geometric sequence. But here, in general, you can say it's Bn. It may not be a geometric sequence.
I forgot some of the.
Yeah, you may forgot, but try to remind yourself, okay, about this part. And I believe you will have to remind yourself for after a few weeks for the real analysis course. Okay, this will be very important in real analysis course.
Okay, thank you.
So this is about the uniform convergence. Now let's go back to our problem. Of course, we want our convergence to be uniform convergence, otherwise it doesn't make sense. Right? Because remember, what do we want? We want it to satisfy our partial differential equation. So if this convergence is not a uniform convergence, then we cannot take derivative term by term. This will be a big issue, right? So here, if we really want this sequence to approximate this f theta, what we do want is not pointwisely convergence. We want the uniform convergence. Okay. So suppose we already find some an such that this kind of sequence can approximate f theta uniformly. Let's see, what do we want for an? Okay, suppose this is true. Let's see what happens. Then that means we can multiply something and take the integral, both sides. And on the right-hand side, we can actually take the integral term by term. Let's multiply e to the minus im theta and integrate from minus pi to pi. And see what happens. On the right-hand side, it is, well, on the left-hand side, it is from minus pi to pi, f theta e to the minus im theta d theta. Okay? On the right-hand side, it is, and from minus infinity to infinity, an e to the in theta minus im theta d theta from minus pi to pi. So what do you get? What do you get from the right-hand side? The left-hand side is nothing can be simplified, right? But what do you get from the right-hand side? Any idea?
Wait, you just basically you just get like e in the power of I multiplied by theta multiplied by n minus m, and because should be its own integral just divided by some kind of a coefficient that we just
Yes. Then what's that?
e in the power of I multiplied by n minus m multiplied by, I don't know, and then divided by I multiplied by m minus n, and then we just like pi and minus pi and we subtract.
Then what's that? What can you see if you plug in pi and minus pi?
Well, we get like e in the power of I multiplied by pi, and we can use the formulas we have, which I constantly forget. Give me a sec.
You don't really need to do that.
The only terms that contains the imaginary part was a sine function, and the sine function was like not really sine function, because there's an integration of sine become cosine, and there's only imaginary part left, right?
You have to discuss in two cases, right? If you divide by m minus n. If m equals to n, then this is just a 1, right? So you know this is 2 pi. If m is not equals to n, this is 1 over I m minus n. e to the I m minus n theta, evaluate from minus pi to pi. Well, did we say that this function is of period 2 pi? Right? This function is of period 2 pi. Then of course, the minus pi and pi, they can cancel.
Wait, sorry, how did we know it's a periodic function again?
Well, what is e to the I m theta? Is cosine m theta plus I sine m theta, right? This is of period 2 pi, this is of period 2 pi, right? Sine and cosine both of period 2 pi.
Oh, okay, and we just subtract them. Okay.
Yeah, right. So what do we have? If m equals to n, it's equals to 2 pi. If m is not equals to n, it just disappears. So the right-hand side is equals to 2 pi times a. That means am is equals to 1 over 2 pi from minus pi to pi f theta e to the I, well, minus I m theta, d theta. It's very simple. It's even simpler than the Taylor series. For Taylor series, you have to take the nth derivative, right? But here, if you want to find this an, you just need to take this integral. Okay, this is so-called the Fourier series, the Fourier coefficient. Of fx. Or you can also denote it as f hat at m. In the future, we may see what's the meaning of f hat. Okay. Now we just denote it as f hat at m, which means the m's Fourier coefficient of f. Okay, any question? And by the way, this is also the reason why we don't use another notation in order to write it. Another notation which is always being used in other literature is well, you always want to write f theta instead of this very ugly, complex, well, imaginary e to the I m theta. Sometimes you also write it as am cosine m theta plus bm sine m theta from 0 to infinity. This is another way to write this Fourier series of f theta. Okay, maybe that I shouldn't write it as equal. Maybe I should write in this notation because they may not be equal to each other. But sometimes in some literature, they use am and bm to denote it as a Fourier expansion, as a Fourier series of f theta. Now you can see that these two are actually equivalent, right? Because cosine theta is nothing but e to the im theta minus e to the minus im theta divided by 2. And sine theta, you can also write it, right? And the reason we don't really want to write it in this way is you don't really have a uniform form, right? If you have this kind of thing, then yes, you will have some similar things like cosine m theta d theta. If you take from minus pi to pi 1 over 2 pi, what you get is am. Similarly, you will get similar things for bm. But then what you need to check is this one multiplied by any other cosine n theta and sine n theta will always give you 0. You take the integral, it will always give you 0. Okay, and minus pi to pi cosine m theta times sine n theta is always equals to 0. But here you can see we can make this kind of notation simpler compared with this kind of notation. But they are talking about the same thing. Okay, whenever you see this kind of notation in some other literature, you will know that they are discussing the same thing. Any question? So right now we say that if you want to find those kind of sequence that's formed by this sine, cosine, or e to the in theta, then such that it converts to f, then it must be f hat n e to the in theta and from minus infinity to plus infinity. It must be in this form. However, what we don't say is this is actually converged to f theta, even pointwisely. So here, let's use this notation to denote that the Fourier expansion of f theta is this one. Okay, the Fourier series of f theta is this one. But now we don't have the convergent property of this sequence. Of course, we want it to converge uniformly. However, this may not be true. Okay, or we want this kind of, let's use another notation. This is a partial sum of f is equals to sum and from minus capital N to big capital N, f hat n e to the in theta will converges uniformly to f. This is what we want. However, I will tell you this may not be true as n goes to infinity. This will not be always true. Okay? I probably will not construct the example for you because the example is quite technical, but if you are interested, you can read it on Stan's book. And we will mention it later. Okay? For what kind of, for some functions f, even f is continuous. You know that if it converts to f theta, since this converge is uniformly convergence, so each terms are continuous, so your f should be continuous. But even your f is continuous at each point, you may still get some Fourier series, this Fourier sequence, it will diverge for any point. This is a very interesting example. And the construction is quite technical, but very interesting. Okay, so last 4 minutes, I'll just tell you several very basic property about the Fourier coefficients. Okay, which probably I will only prove in 1 or 2 words about this this kind of thing. Maybe let me give you an example before we move to this kind of proposition. For instance, f theta equals to theta when theta is bigger than minus pi, less or equal than pi, and this f is periodic of 2 pi. Okay. Then, how can we compute the Fourier coefficient or the Fourier series of this f theta? We know that f hat n is equals to what? Is equals to by our, where is our definition? Is this one? This is our definition. This is our definition of Fourier coefficient. Is equals to 1 over 2 pi from minus pi to pi. Okay, theta e to the minus im theta, well, in theta d theta. Okay. This is easy, right? What you need to do is integration by part. You'll find that eventually our PDE course, the key part of our PDE course are always either integration by parts or Cauchy-Schwarz inequality. Okay, you'll find that eventually. So let's try to do the integration by parts. So if we do the integration by parts and we see this as a derivative, this is a derivative of 1 over I minus 1 over I n e to the minus I n theta, right? So it is, well, 1 over 2 pi times the minus theta over I n e to the minus I n theta. This function evaluate from minus pi to pi plus 1 over 2 pi I n minus pi to pi e to the minus I n theta d theta. Okay, so this part is easy, and this part is you just plug in. And if you plug in, you find that, okay, this pi cancel this pi, this part disappear. Okay, this part just disappear because this one is of period 2 pi, so well, again, it will disappear. This part, if you plug in pi and 2 pi, it cancel, well, pi and minus pi, it cancel this pi, and this will become either, this term will become minus 1 to the power n. Okay, so eventually what you get is minus 1 to the power n plus 1, because you have n plus 1 here, divided by I. This is a Fourier coefficient of f theta equals to theta. Then the Fourier series of this f theta is from minus infinity to infinity, minus 1 to the power n plus 1 divided by I times e to the I n theta. Now you can see it is absolutely not obvious whether this guy converges to this function or not, right? So which means in order to check whether Fourier sequence, whether Fourier series converge or not, is an issue, which is something we are going to discuss next time, okay? About what kind of function this Fourier series may converge to this function.
So actually what we're doing is like, first of all, we don't know that the Fourier series converges or not. We're just trying to apply those kind of mechanics in.
Yes.
As soon as when we get the result, we will start to check the convergence or not.
Yes, because you see, the logic is like this. We want some convergent Fourier sequence so that it can solve our PDE, right? And we try to check if the sequence converge, then what kind of sequence you should get for the coefficient. Then you got, okay, the coefficient is uniquely defined, is uniquely determined by your function. So the only thing you need to check is, okay, since it's uniquely determined, then whether it converges or not. Whether this uniquely determined coefficient makes your sequence converge or not. If it converges, then we close this circle. Otherwise, we might be in trouble.
This is actually like a trial error.
Exactly. This is like a trial. This is exactly like a trial. This is nothing but we just make a guess, and then eventually we want to close our guess, make it as a proof. Okay? So I'll be here until 6, but we will end here. So discuss more on Thursday. If you do not have any questions, just, well, you can feel free to leave. Otherwise, you can ask me and I'll stop the recording.